We will start with the new chapter, and it has been quite some time that I have not uploaded any video. I was busy in my work stuff and other things, but let's get started. This is again, I have already spoken a lot about module 2. Now we will go to chapter 9, which is on natural language processing. So I'll try to finish this in a single video, but if it becomes very long, I can take I can break this down into smaller sections and subsections also. So before we get started on NLP, NLP is a very wide subject. There are a lot of things in NLP, but I'll try to go reading by reading within the perspective of what GARP thinks you should know about NLP. Okay. So NLP, as you know, stands for Natural Language Processing. Now it has three words: natural language and processing. So now what does this mean? So language, you all know, language is a means of communication between two entities. Initially we could have said human entities, but now it can be machines as well. So this is a kind of a communication protocol between two entities where almost everything and anything can be explained and narrated and communicated. Then why do we call it as natural? Okay, why, if this is a natural language, what is an unnatural language? So why we call it natural is because most of the languages that humans communicate, or humans started those language for communication, it evolved and it started from spoken form, and then it went into written form. Around 3000 years back, there was no written form, and then written form started, but phonetically, verbally, languages were in use from a very long time. Natural languages are ambiguous. So what is an unnatural language? An unnatural language can be something like a Python or a Java, or those kinds of computer languages. Those humans don't use those kinds of languages. Natural languages are ambiguous, and we as humans, we understand and we comprehend that ambiguity, and we are very good in resolving it. So if I tell my wife or my son that I am going to a bank, they will know that since it is an apartment in Pune, and it's a weekend or Saturday, they know that I am going to go to a financial institute to process some work. But if I'm on a holiday, if I'm in Rishikesh, and if I tell my wife and son that I'm going to a bank, they may know, yeah, it's a river bank. So that kind of ambiguity happens in natural language, but we as humans are good in resolving it. Processing means that we want to make the computers understand that language, or we want to process it using some mathematical or logical forms. So processing can be understanding of that language, because we're talking about natural language. It can be generation of the particular language, or it can be the inferencing of that particular language. There can be a subtle difference between the three, but yes, this is how it is, and that's why it is also being referred to as NLU, NLG, and NLI in different aspects, in different kinds of use cases that natural language needs to go. So NLG is more like your generative AI, where new tokens are getting generated. You are asking questions, and you will get some rightful responses using LLMs like OpenAI models or anything else. Okay, so that's what natural language generally is. It is not that GARP wants you to understand this philosophy of what a natural language is, but it is good to know what natural language processing means before we start getting into the depth of things. So generally what happens in case of a natural language processing, there is a kind of a linguistic digital information that we get as an input, and then we process it with NLP techniques, tools and techniques, and then we can get some kind of an inferencing details, whether it is understanding, generation, or anything else. So we give some insights, there is inferencing, there are insights that somebody wants to see, or there can be whatever it is, classification or any other stuff. Now this NLP in the middle, this can be broken down into multiple, and this is what Garp wants you to know, that the subcomponents or the processes in the pipeline of NLP starts with tokenization. Then there is something called as a pre-processing. Then you can call feature extraction, and then there can be models. Okay, and then models will give you output as insights. And the pre-processing can be broken down into, as per Garp, 3 parts: stop word removal, then it talks about stemming, and then it talks about lemmatization. Okay, so this is as per Garp. We can break this down further, or we can break this down by other means as well, but I'll stick to how Garp has officially put this into these kinds of processes. Now tokenization means that your natural language, a sentence that you and me speak, that sentence is a combination of words. So if I'm saying that that I am teaching a course on NLP today. Okay, so this is a sentence that I am talking about, and then you and me understand what this means. So the first step, which is tokenization, what it means is it tries to break down this sentence into individual entities. I am not specifically saying words, because sometimes one word can be broken down into 2 tokens. So it can be, I is different, am is different, teaching, depending upon the tokenizer, but most of the tokenizer will say teach is different, ing is different, etc., etc. Okay, NLP as an acronym can be broken down separately, NL and P, or it can be taken together, NLP, based on how the tokenizer wants it to break. So tokenization, the intent of the tokenization is to break down a sentence into individual tokens. Okay, you may have seen that, or you may have heard that most of your language models, whether it is LLM or anything else, they'll say that they'll try to teach you, or they'll try to tell you that the size of their model is so much. Okay, so it can say that I can process 4,000 tokens, the free version of GPT, which came a couple of years back. So it also talks about their limits in terms of tokens. So once you have the tokens created, the second, which is the pre-processing, it has something called as stop word removal. So there are a set of words that in NLPs are referred to as stop words, which don't make much semantic sense, and even if we ignore them or remove them, it really doesn't make a lot of difference in the end-to-end execution of that particular use case. So things like am and or to, etc., in this particular case, they are so omnipresent in almost all the sentences, all the documents, that even if we remove them, it will not make much of a difference, and computationally it might become easier to process. Okay, so that's how we do stop word removal. Stemming and lemmatization, both of these things, they do the same thing. So what happens if there is a token and you want to take it to its root form? Okay, so when I say root form, what it means is that, let's suppose we are talking about something called as swim. Okay, now swim can be swimming, it can be swam, it can be swims, or it can be some other forms of this verb which can change based on tense, based on gender, based on some other things. So when I have to take the token into the root form, there are two ways to do this. One is called as stemming and the other is called as lemmatization. Now lemmatization is more of a linguistic phenomena, and stemming is more of a computational phenomena, which means that when I take a token from here to its root form, it goes via some set of rules. Okay, like if there is an ing in the end, you remove it, etc., etc. And if I have to take it via this, there are some linguistic processings, or linguistic dictionary or those kinds of things which takes it to a root form. So both of these things do the same thing. Most of the new models prefer lemmatization wherever needed, but in the past, stemming has also been used for going back to the root form. So that's on the stemming per se. The next is the feature extraction. So what happens that we are talking about text here, and text is a mixture of words. Now as such, computer doesn't understand words, it will only understand numbers. So how do we represent words into a kind of a numerical representation? Because unless we don't do a numerical representation of a textual substance or a textual entity, computers cannot process it. So that's generally called as feature extraction. The conversion of a word to a numerical entity can be done by multiple ways. One is called as one-hot encoding, where you find out the vocabulary and then you see whether the word is there or not. Vocabulary is also sometimes called as bag of words kind of a technique. There are some kind of static word embedding techniques, like your word to vec and glog and those kinds of things. We are going to talk more about this in the next chapter, which is on the generative AI. And then there are transformers, which also do embeddings, but these are more dynamic or contextual embeddings, like your BERT and other kinds of things. So the conversion of a textual word into a numerical representation of the same word so that it can eventually get processed by a computer is called the feature extraction. That's how Karp also tells this. And then there is modeling. So there are these days everybody is using neural networks, and there are a lot of neural networks which can be used for processing words, like your words or sentences or anything, like your transformers. Transformers have been very popular in language processing, and all of these LLMs, etc., are nothing but your decoder only transformers. Okay. And then there can be traditional machine learning techniques like your naive Bayes or other kind of techniques which can be used to process linguistic stuff, like your if you want to, we'll talk about this naive Bayes in this chapter itself. I'll give you some kind of a philosophy of what naive Bayes is and what kind of problems it can solve. The GARP is going to talk more about if you get emails and then there are some emails which are spams, how do you identify which are my spams and which are not so spam, and which are my important emails. So those kinds of use cases can be also be done by machine learning models, the traditional machine learning models like your naive Bayes. So that is about your complete pipeline of processes that NLP can take to process a linguistic element end to end. Okay, so let me go to what this talks about. The next step is about this feature extraction, which we said that it is nothing but conversion of a linguistic or a textual element into a numerical element. So let's start with the when hot encoding. That's our first step. So what happens? Let's suppose there are two documents. It says, and when I say document, it can be single sentence, a couple of paragraphs or couple of pages, etc. But for simplicity, we'll take a document as a single sentence, so that it becomes easier for me to explain to you, and that's how GARP will also consider documents as a single sentence itself. Okay, so document one is it's a good day today. And document 2 says that days are getting hotter. Days are getting hotter, which is not good. Okay, so if these are your two documents, then how do we do one hot encoding? Is the first step is we create a vocabulary. So when I say vocabulary is nothing but you take the combination of all the words that come across all these documents, and we are only talking about two documents here, but there can be more than two documents. So we just go word by word, and then if there is a repetition, we don't add that to a vocabulary. So since it is a set, okay, so I say it's and when you do this kind of a conversion, you can also, and since there is tokenization etc. involved implicitly, which we spoke about, so it can be put like it and ss separately. Okay, but anyway, let me put it like this right now. It's a good day today, and then I said day is already here because days I'll take it to the root form, stemming out lemmatization, and then I'll say are getting, I'll say get a hotter, so I'll say hot which is not good is already there. Okay, so that's how we'll create the vocabulary, and once I have the vocabulary created, I can vectorize these both documents. So document one in a vector form is going to be so now that we have the vocabulary, we need to represent this vocabulary, and vocabulary is going to be consistent, so we need to represent the occurrence of a word in a vocabulary once or twice. So it happens once, good day today, and then all of the other things they are going to be zeros. And document 2 in the vocabulary form can also be represented similarly. So the all of this will be 0, and then there will be when. Okay, based on what occurs and what do not occur. Since there are no repetitions, I don't see any repetitions in both these documents or sentences. There is everything is either when or 0. But if there is something happens twice, so if it is which is not a good thing or something, then then we can put 2 also sometimes. But anyway, so that's how we do one hot encoding for numerical representation of these documents. We can also normalize these vectors. Why do we normalize? Because the size of the documents may not always be the same. Okay, so in that case, it is always good to normalize these documents so that the vectorization is independent of the size of the document. So how do we do it? We generally we take this vector which we have, and then we divide this with the squares of individual elements square rooted. Okay, so in this particular case, if there are 1 2 3 4 5 ones and all zeros, we add 1 square plus 1 square, and that becomes 5, and then we do the root, so it becomes root 5, and then it is the vector. So everything becomes 1 upon root 5, 1 upon root 5, and 0 divided by anything anyway is 0, so 0. So that brings both these vectors at par, and that's the normalized vector representation of these two words. Okay. Then the next reading in GAR. So this is when hot encoding, the most basic form of, or the bag of words approach, which is the basic form of numerical representation of text into vectors. The next is the dictionary approaches. What happens when NLP was new thing and people were trying to find out ways and means to process text, they started with these dictionary comparison kind of approaches, where they were building some kind of lexical inventories, I would say. And they were like your, they were different for different languages. For English, there is something called as WordNet, if you have heard. But what happens is, there is a particular word, let's suppose it will have that these are its synonyms, these are its probably antonyms, this is the polarity of the word, whether it is a positive word or a negative word, etc., etc. So there are going to be a lot of human annotated information for a particular lexical word. Okay, so if there is good, let's suppose the word W is good, then your synonyms can be great and excellent or nice and those kinds of things. Antonyms can be bad, etc., etc. And since it is good, the polarity is going to be positive. So that's how most of these dictionary approaches started, with building these large human annotated corpus, and these were used to do a lot of NLP, and for especially for use cases like your sentiment analysis. When you have a paragraph and somebody is saying that, I went to so and so cafe and I ordered for a coffee and some croissant, and then I had it, and the coffee was tasting great, better than anything that I have ever had in my life before. So when you want to process all of that paragraph and just want to tell the consumer of that information whether it is a positive or a negative sentiment, what people used to do is, people used to take those words one by one, and then you find the polarity of those words. Okay, and then there can be few words which are positive, there can be few which are neutral, and then can be a few which are negative, and then they used to sum everything together. Okay, sum of polarity, and whatever was the end, they used to tell that, okay, this is either a positive or a negative case, which was doing well. So it was better than not doing any analysis, but it had its own demerit. For example, if you tell me, how has been your experience working with so and so customer, and I say it is not good. Okay, so not good means bad, which is negative, but not is your negative polarity and good is your positive polarity, and if I sum this together, it may become neutral. Okay, so sometimes if you use a lot of negations along with some keywords, your lexical approaches or dictionary based approaches may not work very well. So these are some of the problems. There can be more problems related to this. Have a read at what is there in the book, but I have told you that this is what a dictionary based approach is. The next important reading or concept is when they talk about this n-gram model. So in case of NLP, we are trying to create a language model. Okay, now we are trying to create a language model, and if you talk about all of these ChatGPT, etc., etc., they also call it as LLM, where though the first L stands for large, but this LM stands for language model, which is nothing but what I am referring to here. So now language models, based on the amount of compute and time and the other kind of resources you have, you can again let me give an example. If I say that I am traveling to New Delhi, okay, so if I want to process this sentence, I can process, when I do tokenization and other things, I can process this sentence by taking one token at a time, which I called as a unigram model. So uni means one, gram means, that's a singular model. So I am taking one is different, am is different, and traveling or travel to, and then new, and then Delhi. Okay, so that's a unigram model. I can also create a bigram model where I take two elements together and I say I am, and then I say am traveling or travel, and then I say travel to, and then I say to new, and then I say New Delhi. Okay, and then there can be trigram and quadgrams, etc., etc. The point I'm trying to make is that when you try to process two words together in a natural language, especially in this example that I'm taking, when you say new is different and Delhi is different, this new can be interpreted entirely differently. Okay, but when you take New Delhi together, we all understand that okay, this stands for a particular city in India. So as your as your n becomes bigger in n-grams, your processing becomes better, but then your compute also is required more and more. So those are the language models and how we can create those kinds of things, or those kinds of complex or bigram, trigram, quadgram models. The next important reading in GARP is, and which may take maybe another 10 minutes or so, or 5 minutes, is called TF-IDF. Okay, you just there is a possibility that you may also get a numerical around it, but let me try to explain. This is not difficult, very easy. So TF and IDF, or TF-IDF, as it stands for, it has two elements. One is a TF, one is an IDF. So TF stands for term frequency. Okay, and IDF stands for inverse document frequency. Okay, so now what happens is that you have a set of documents, okay, D1, D2, D3, and so on. When I say document, it is nothing but a sentence of words, or I'll say W11, and then I'll say W21, W22, Wn dash 2, etc., etc. Okay, so when I say term frequency, the term frequency is always for a particular word in a particular document. Okay, so this is J. There are J different documents. For when I am saying term frequency of word when in a document when, it means that I am talking about a particular word and a particular document, which is nothing but the number of times the word is appearing in that particular document divided by the document, the number of terms in the document itself. Okay, why do we do this? Because there can be long documents, there can be short documents, and in longer documents, a word being there or not being there may not be so significant as it is in a shorter document. Okay, so that's why whenever we calculate term frequency, we calculate the frequency of that word in that particular document, how many times the word is appearing in that document, and we divide it by the total number of words in that document. Okay, so that's how we do this. So there are 10 words here, and assume every word is unique. Okay, so there is a document D which has W1, W2 up to W10, and let's assume for now that none of the words repeat. Okay, so then if I have to find the term frequency for these words, it's going to be 0.1, 0.1, 0.1, because it's going to be 1 upon 10, 1 upon 10 till 1 upon 10. Okay, so that's the term frequency. Now let's talk about idea which is inverse document frequency. Okay, so since it already says it is inverse document frequency, it is going to be reciprocal. So that means that we will take the number of documents in the numerator and we'll take the frequency in the denominator. So frequency in the denominator means that the number of documents, let me first write it in a text form and then I'll write it in the mathematical form. So I'll say total number of documents and number of documents in which a term appears. Okay, so this is your number of document is this, and let's suppose this di, I'll say sigma. So di is either 1 or 0. So it means that if a particular term is present in a particular document, it becomes 1, otherwise it is 0. So if you have, let's again say that you have 5 documents and a term is happening in only 3 out of those 5 documents, then it becomes 5 upon 3. Now to make this more interesting, or that's how generally IDF operates, we take the logarithm of this ratio. Okay, so we do d upon di and we take the logarithmic value and to base e. Okay, and this is also written as ln and d upon di. So that's the inverse document frequency, and as you see, inverse document frequency is for a particular word. Okay, of course it's for a particular word, but it is not specific to a document. So if I say that there is a word called as New Delhi, and in the corpus the inverse document frequency for New Delhi is, let's suppose, 0.03, it implies that it is going to be 0.03 for all the documents in that corpus. Okay, so that's what an inverse document frequency is, and then generally you try to multiply term frequency with inverse document frequency to get the final numerical representation for that word, which already accounts for how frequent the word is across documents and how frequent the word is within that document. So I hope you understood this, but this is an interesting, and this is still used, and this works well even with the new generation models, and a fantastic thing. In fact, I went to a conference last year, ACL conference, and I was hearing a lecture or a kind of a talk by one of the professors, and he was the one who had invented DFID. Okay, I forgot the name though, but yes, it is still relevant, and it is phenomenal. But this is how it is, and you may want to do some exercises which are there in your book, but it's not that difficult to understand. Okay, so that's how TF-IDF is. Let's do next. Let's see what we have to do next, and then we'll try to end this chapter. Okay. Okay. So after TF-IDF, GARP tells you that there are some other machine learning approaches that you should understand, you should know. There are more complex approaches that are present. Let me take this little upwards. Okay. There are more complex approaches that are present, but that will some of those embedding approaches like CBOW and skipgram we will read in chapter 10. But for the purpose of chapter 9, there it talks about things like naive Bayes classifier. I think we have already discussed this, but I will still discuss this with respect to how text gets processed. Okay. So what happens in naive Bayes classifier is that the only assumption of naive Bayes classifier is that the entities that you are trying to process have to be independent of each other. And in case of an email, if we are trying to see if the emails are spams or not so spams, the textual elements in those emails or the words or the tokens in that emails are independent of each other. That's the assumption. Okay, but what it means is that let's suppose we are trying to classify a particular document into some set of classes. Let's suppose there are C1, C2 and C3 classes. Okay. And then so the probability of the occurrence of C1, C2 and C3 will also be different. Okay, so there is going to be some probability of C, so which is probability of C1, C2 and C3. It can be, let's suppose there is a 40% probability that it is in class 1, 30% probability that it is in class 2, and 4 and 3 70, and 30% it is in class 3. Okay, that's the overall probability. Okay, so for example, your email being generic email but not that important is 40%, it being spam is 30%, and it being very very important is also 30%. So that kind of a classification I am talking about. So that's one element in naive Bayes, which I let's call as a probability of a particular category overall. Okay, overall. And then there is something called, now we are talking about multiple documents. So document is nothing but an email. Okay, there is going to be probability of a document, and then there is going to be probability that probability of C given the document. Okay, so how likely is it going to be is it going to be some kind of a category given that this is a document? So these are the three things that we need to calculate, and once we have this thing in mind, we will, since this talks about Bayes theorem, so of course there is going to be a Bayes formula. We are eventually going to calculate what is the probability given a document, what is the probability that it belongs to a category C. In this case, it can be C1, C2 and C3. Okay, and the probability that a particular email is a spam is nothing but the probability of particular category that it is in that email multiply by probability of C, and we will divide it by probability of D. Okay, so that's the basic Bayes theorem. Okay, so this is your basic Bayes theorem formula, and you do this for so in this particular case we'll have to do this for all three: probability of C1 if it is D, probability of C2 and probability of C3, and then we will try to normalize all of them and see which one is the maximum. Okay, so that's how we will try to find out what it is. Let me see if there is an example I may want to take. and then based on that, I will not get into the depth of the example, otherwise it will take me 1 hour to just go through the example itself. However, if you find any problems, you can put that problems in the comment, and if there are multiple or too many people trying to are not being able to figure out how this entire thing or how this Bayes theorem works, then I'll try to see if I want to do a working example for a Bayes theorem or things like that. But believe me, it's not very hard to get once you get into the concrete examples of D1, D2, D3, and then particular words inside each of those documents, and then you see, okay, that in a span, there can be terms which are more, say, sexually explicit, or terms which are more, say, financially explicit. So that helps you to find out the probability of D by C and those kinds of things. Okay, and so once you have all these three terms, then it is nothing but doing some kind of a comparison. So that's the naive Bayes classifier. I will stop here, not get into more details of what naive Bayes is, and as I said, I will be more than happy to take a working example in a separate video if I get those kinds of comments that yeah we want those kinds of things. Okay, there are two more things that I will teach today, and then after that we will close this chapter. The one thing is that the second last reading, what Garb talks about is word embeddings, and we spoke about this already. We talk about when hot encodings, which I explained. Then there is there are bag of words, which is similar to one hot encoding. We also spoke about numerical representation of static word embedding. We will talk more about it in the next chapter. What happens? Let's suppose there is a word. Okay, let's suppose there is a word W, and there are some words that will precede it, and there is some words that will come after it. So let's suppose this is Wi, so this is going to be Wi minus 1, Wi minus 2, and so on and so forth, and this is going to be Wi plus 1, Wi plus 2, and so on and so forth. Now if I want to find calculate the probability of Wi being Wi, when I know that it is getting preceded and superseded by these words, that is, I am trying to converge to Wi, knowing that it is being preceded by some words. That is called as CBOW, continuous bag of words. And if I do the opposite, knowing Wi, if I try to find out what it precedes, or what are the words that come before it and after it, that is called as skipgram. Just take this on a very high level for now, because I am going to talk about it in a little more detailed manner in next chapter when we talk about generative AI. So these are the two techniques in case of word embedding, static word embeddings, and then there are more techniques which are called as contextual embeddings, which what they do is that it takes into consideration the entire sentence or a document, and then try to preserve the context when it comes to finding the embeddings of a particular word. Now in this particular case, the bank or the river bank and the bank as a financial institute will not be discriminated. It will still have the same embedding, because it is only for it's at a token level. But in case when we try to do the contextual embeddings of a longer piece of text which knows what is the context, in that case a bank, a river bank, and a bank in a financial institution, or apple as a fruit or apple as a company, will behave differently. So those are contextual embeddings. These are there are examples like BERT, BERT, and other embeddings. OpenAI also have their own embeddings, etc., etc. Okay, Da Vinci or other models, or Titan models by AWS, etc. So those are all contextual embeddings which are used today. So that's on word embeddings. The last reading, as per GARP is, so we will not talk so much about contextual embedding, but we'll talk about CBOW and skipgram in next chapter. Okay. The last reading in this chapter is about how do we evaluate NLP applications. Okay, so now if it is a kind of a classification, as we're talking about emails, whether it's a spam or not so spam, then you can again go back to those precision and recall and the Arvin scores or AUC, etc., etc. So those are the ways in which you evaluate a any form of a classification model. But then sometimes there are more specific NLP use cases, like let's suppose there is a translation. Okay, so in case of a translation, you need to find scores like BLEU, BLEU. Okay, and then there can be things like paraphrasing. Paraphrasing, you can use score like Meteor. Okay, so what happens in these kinds of techniques for NLP evaluation is that there is a machine generated sentence, and then there are annotators, there are human generated sentences, and then it tries to find out the overlaps between what is generated by the machine and what has been annotated by the human in a smaller group of course. If the machine translation needs to be done for say million sentences, we cannot ask humans to annotate the million sentences. We'll only take 500 or 1000, and in those 500 and 1000 we'll see how a machine is translating versus a humans are translated, and then it will try to find the overlaps also based on, we spoke about n-grams. It can be bigrams or unigrams, and based on that we can get a BLEU score. A BLEU score of 35 or more is generally considered nice. Okay, if it is, so this is for words like or languages like English. If I have to do a translation, evaluation for languages like Hindi, I may be better off using scores like CHRF, which are more character by character rather than word by word, because in Hindi we have a lot of matras, and the vowels or the way vowels and consonants come together with each other. Sometimes it becomes more complex to do a word by word analysis rather than doing a character by character analysis. In case of paraphrasing, we use matrices like Meteor, because Meteor also, while it is also doing a similar philosophy, but it is also trying to find out the synonyms, etc. So since paraphrasing is more about talking about the same thing in a different manner, we need to be wary about whether if I'm using a synonym and the humans are using some other synonym, it eventually means the same thing. So it also goes and checks if synonyms that are used. So there is some kind of a linguistic or a lexical analysis done if synonyms are used or not used. So that's where we use Meteor. There are a lot of other matrices, but in NLP the evaluation metric depends upon the use case that you are being referring to, and evaluation itself is a kind of a complex phenomena in kind of a NLP application. So that brings us to the end of this chapter, chapter 9. We will start with chapter 10 next, which is the Gen AI, generative artificial intelligence, and that would be the last chapter for module 2, and then we will start with the module 3 and 4 and